In this lecture, we are going to discuss about step response of a second order system. So let's see first what we are going to cover. So we are going to discuss about the roots of a second order system. Then we'll see the effect of damping ratio on the performance of a second order system. Then we are going to derive the time response of a second order system when we are applying step input to it. Then at the end, we'll derive the time response specification of second order system. So let's start the second order system. We are aware of when we are having transfer function for any system, we need to see the denominator and the highest value or highest power of s we need to see, and if it is 2, then we can say that that system is second order system. So example of second order system we can have is a spring mass damper arrangement. So here spring we represent by K and damper we represent by C, mass by M. So when we apply force and we try to derive the equation of motion of this system or mathematical model of this system, so it will be mx double dot plus cx dot plus kx, and that is equal to applied force, that is F. So after deriving the equation of motion, we can apply Laplace transform and we can get the transfer function for this system, and that will be the output upon input. So here output we can have in the form of displacement, that is x. So the transfer function for this system is x of s upon f of s, and that will be equal to 1 by ms square plus cs plus k. So this already we have discussed how to get the transfer function for a given system in previous lectures. So based on that, we can determine the transfer function for this system. So this is how it will look like. For a second order system, we can also write the closed loop transfer function in a standard form as C of s upon R of s, and that will be equal to omega n square divided by s square plus 2 zeta omega n s plus omega n square. So this is the standard form or standard transfer function for any second order system. Now this standard form we can also write in a block diagram by using this arrangement. So we'll be having summing point, and after that we'll be having open loop transfer function that we can write in this form, and then we will be having the feedback signal here. So we will be considering for this case as unity feedback. So by reducing this block diagram, we can obtain the closed loop transfer function or standard closed loop transfer function for second order system in this form. So let's derive that. We are having g of s is equal to omega n square divided by s plus 2 zeta omega n. We can also consider here h of s, which is unity. So we will be having this transfer function as g of s into h of s, and it will be equal to same value omega n square divided by s in bracket s plus 2 zeta omega n. Now in order to write the closed loop transfer function for this system, we can write it as C of s upon R of s, and that will be equal to g of s upon 1. Now whether it will be minus or plus, that depends upon the feedback signal. So here feedback signal is negative, so we will be having positive here. So 1 plus g of s into h of s. So by substituting value of g of s and g of s into h of s in this equation, we can get the closed loop transfer function. So it will be omega n square divided by s plus 2 zeta omega n divided by 1 plus omega n square upon s in bracket s plus 2 zeta omega n. Now we have to simplify this expression, so let's do that. So in above we will be having omega n square upon, now we can multiply this s inside if we want, so let's do that. So it will become s square plus 2 zeta omega n s divided by, now here we can cross multiply this denominator with 1. So we will be having s square plus 2 zeta omega n s plus this term, that is omega n square, and again in a denominator of this value will be having s square plus 2 zeta omega ns. Now here the denominator from this term and denominator from this term is same, so we can cancel both of them. So we can cancel here. Now we will be having closed loop transfer function as omega n square upon s square plus 2 zeta omega ns plus omega n square. So this is the closed loop transfer function for second order system that we have seen here. Now let's determine the pole of this transfer function. So pole of this transfer function will be equal to the roots of this denominator here. This denominator will be called as the characteristic equation because this denominator is going to give us the pole for this system, and pole is that value of s which is going to make the transfer function infinity. So let's determine the pole here or the roots of this characteristic equation. So it will be s square plus 2 zeta omega ns plus omega n square, and that will be equal to 0. So now in order to find the root of this equation, we need to use the factorization formula. So that is, we will be having two roots here, that is s1 and 2, and it will be equal to minus b plus minus under root of b square minus 4ac divided by 2a. So we can use this formula in order to find the roots of this equation. So let's see what a, b and c value we are having from this equation. So a will be equal to the coefficient of s square, so that is 1 here, so a will be 1 here. Similarly, b will be the coefficient of s, so that value will be 2 zeta omega n, so b will be equal to 2 zeta omega n. Now similarly, c will be the constant value, so that is this omega n square. So this one is c and this one is b here. Now let's substitute that in this equation to get the two roots of this equation. So it will be minus 2 zeta omega n plus minus under root of, now again 2 zeta omega n will be having here, but its square we need to take, so it will be 4 zeta square omega n square minus, we are having 4 as it is, a is 1 here and c is omega n square, so it will be 4 into 1 into omega n square divided by 2 into 1. So now let's simplify this expression further. So what we can do, we can write it as minus 2 zeta omega n. Now plus minus, we can take 4 and the common term outside this root, so it will be 4 will become 2 and omega n square we are having, so it can come out from both these terms, so we'll be having omega n, and in a root we will be having zeta square minus 1 divided by 2. So now further we can simplify this expression by taking 2 common from the numerator and 2 we are having in the denominator, and we can cancel both of them. So it will be minus zeta omega n plus minus omega n under root of zeta square minus 1. So this is the value of roots of this equation, or we can say pole of this transfer function that we are having here. So the two roots we can write it as s1 is equal to minus zeta omega n plus omega n under root of zeta square minus 1, and second root is s2, and that is equal to minus zeta omega n minus omega n under root of zeta square minus 1. So we can see here the transfer function depends on the value of these two roots, and these two roots depends upon the value of zeta. So now further we can discuss based on the value of zeta, that is damping ratio, how system is going to behave. So now we'll discuss the effect of damping ratio on the performance of second order system. But before that, let me write the value of S1 and S2 here. So S1 we got as minus zeta omega n plus omega n under root of zeta square minus 1, and S2 we got as minus zeta omega n minus omega n under root of zeta square minus 1. So we got these two values. Now let's see when we change the value of zeta, how the roots are going to change, and based on that we'll see how system is going to behave. So when we are having zeta 0, that system is called as undamped system, and for that we are going to get S1 and S2 as imaginary. So let's see, if we substitute zeta 0 here, so this term will vanish and this term is also going to vanish, and we will be having here, if we substitute zeta value 0 in this root, so we'll be having omega and root of -1. So root of -1 is nothing but a complex term, so we will be left with omega n j here, and we will be having minus omega n j here. So both the root, when we are having zeta 0, will become imaginary. These value we can plot on S plane, that is a complex plane which normally used to plot Laplace transform. So here, since S1 and S2 is imaginary in nature, so we will be having both the value on imaginary axis, and since one is positive, so it will be above here, another one is negative, so it will be plotted below here on imaginary axis. And the response of this kind of a system we can see here in this graph. So with respect to time, we can see that how output is oscillating. So whenever we are having zeta is equal to 0, that means there is no damping in the system. So if we excite that kind of a system, so it will going to give us output continuously with respect to time. So here we can make out like when we can have this kind of a response by observing the value of zeta. So if it is 0, we know that it will be having this kind of a response. This is also called as an undamped response. And if we know the roots of or the poles of a system are imaginary, then based on that also we can say that the system is an undamped system. So in this way we can use the value of zeta and also the roots in S plane where they are lying. So based on that we can predict the response of the system. Same way we can have zeta lying between 0 and 1. So that kind of a system is called as an underdamped system. So in that case, what is going to happen? Let's see. So in that case, we will be having some value of zeta. So for that case, we will be having S1 is equal to say minus zeta omega n. Then we will be having plus omega n will be as it is. And now here zeta value is lying between 0 and 1. So if it is anything between 0 and 1, so it will going to give us a value which will be a negative with root. So that will going to give us a complex number. So here we will be again having value j, and similarly we will be having S2 also similar. So zeta omega n, but here value will be negative omega n j. So if we see here, so S1 S2 are what? They are complex conjugate of each other. So from this root we can say that whenever we are having zeta for any system lying between 0 and 1, it will going to give us the roots of that system as complex conjugate, and that we can plot in S plane in this way. So say this is S1, this is the pole, so it will be having both value, the real value that is along real axis as well as imaginary value that is along y axis. So in this way we can plot a conjugate in S plane, and similarly we can plot S2 also in a similar manner. So we will be having both the poles in this way on S plane for this kind of a system or underdamped system, and the response of this kind of system we will be having here in this nature. So with respect to time, system will going to give us output, and as the time progresses its output will going to settle down to some value. So this response is called as underdamped response. So based on the value of zeta and the nature of poles, we can predict what will be the response of the system. Same way we can have zeta is equal to 1. So in that case, let's see what will be value of S1. So in S1, if we substitute here zeta is equal to 1, so it will be minus omega n, then we will be having plus, and here since we are having zeta as 1, square will be again 1, so 1 minus 1 will be 0. So this term will vanish and we will be having only answer as S1 is equal to minus omega n. And similarly for S2 also we will be having value as minus omega n. So here we can see that both the roots are same, as well as they are real, as they are not having any complex part. So whenever we are having zeta is equal to 1, that kind of a system is called as critically damped system. And for that system, we will be having poles or root of the system as real and repeated. So again, these roots we can plot on S plane in this way. So both the root will be at same place, and that too on a real axis. And this is how the response of these kind of a system behave. So with respect to time, when we provide the input, it will gradually increase and stabilizes to the required output. So this kind of a response is called as a critically damped response. Next, we can have zeta greater than 1, and this is called as a overdamped system. So let's see what is happening with S1 and S2. So here S1 will be equal to, now we will be having zeta value more than 1. So we will be, let's write it as minus zeta omega n, but here zeta value is greater than 1. Then plus omega n under root of zeta square minus 1. So here zeta will be more than 1. So this root will be positive. So here both the values are real. Similarly for S2 also, it will be minus zeta omega n minus omega n under root of zeta square minus 1. So here both S1 and S2 are real roots, but of course they are not repeated because they are different. So similarly we can plot these roots on S plane. So as they are real roots and they are not repeated, so we will be having this kind of plot. So here we can see the response of this kind of system. So here the output will going to gradually reach to the required output. So if we compare with the critically damped system response, this response will going to take more time compared to a critically damped system to reach to the required output. So in this way, if we are having the information of damping ratio of system, based on that we can directly predict the response or the nature of response of the system. Similarly, if we are having the information of position of pole in S plane, so based on that also we can predict the nature of the response of the system. It is also vice versa. If we are having the nature of the response of the system, we can predict the zeta value as well as the position of poles in S plane. So in this way we can use these information to predict the behavior of the system with respect to time. Now let's derive the time response of a second order system when we are applying a step input to it. So we'll be determining C of t here. We also know that how to represent step input in a time domain. It is written as R of t is equal to U of t. We can convert this into complex form by taking Laplace, and in that case it will become R of s is equal to 1 by s. And the transfer function for second order system we are having as C of s upon R of s is equal to omega n square upon s square plus 2 zeta omega ns plus omega n square. Now this expression we can rewrite in the form of output as C of s is equal to omega n square into R of s divided by s square plus 2 zeta omega ns plus omega n square. Now let's substitute value of R of s, that is 1 by s here since we are considering step response. So C of s will be equal to omega n square divided by s bracket s square plus 2 zeta omega ns plus omega n square. Now here we need to find C of t. So we need to take inverse Laplace of this term in order to get C of t from C of s. So for that we need to arrange this term in a way that we can take the inverse Laplace of it, because we need output in the form of time so that we can substitute time and we can get the output at that time. So for that we need to take the inverse Laplace of this term. So right now it is not in a standard form, so we cannot take the inverse Laplace directly. So what we need to do? We need to do some mathematical operation here so that we can get this expression in the form where we can apply the inverse Laplace. Now here also we need to be careful that for what type of system we are deriving the response. So right now we are considering underdamped system because most of the system that we see around us are underdamped. So we will be having zeta value lying between 0 and 1. So based on this one we will be deriving the output equation. So we can rewrite this as by applying partial fraction. A by S plus BS plus C divided by S square plus 2 zeta omega ns plus omega n square. So here we are having C of S as this value, so we can substitute here. So it will be omega n square divided by S in bracket S square plus 2 zeta omega n s plus omega n square, and that will be equal to this term here. So A by S plus BS plus C divided by S square plus 2 zeta omega n s plus omega n square. Now here, in order to write in this form the C of S, we need to find the value of A, B and C. So here what we will do, we'll cross multiply this term and we'll try to cancel this denominator. So it will be omega n square upon S in bracket S square plus 2 zeta omega n s plus omega n square, and it will be equal to A in bracket S square plus 2 zeta omega n s plus omega n square plus S in bracket B S plus C bracket closed divided by S in bracket S square plus 2 zeta omega n s plus omega n square. So here denominator is same, so we can cancel, and now we will be having omega n square is equal to, now let's multiply A inside here and S in this bracket here. So it will be AS square plus 2A zeta omega ns plus A omega n square plus BS square plus CS. Now next thing that we have to do here, we need to arrange this term considering S square term together, S term together and constant together. So let's do that. So on left hand side it will be as it is omega n square, that will be equal to, so here S square term we are having here as well as here, and similarly S term we are having here and here, and the constant term we are having here. So let's write S square term together, so we can take S square common. In bracket we will be having A plus B. Similarly we can take S common here, so it will be plus S 2A zeta omega n plus C plus A omega n square. So now we are having all S square term together, S term together and constant together. Now we have to compare if we are having S square term on left hand side with S square term on right hand side, similarly for S also and similarly for constant also. So here we can see that we are not having any S square term on left hand side, so it is as good as being 0 S square, plus same way we are not having S term also on left hand side, so we can put here 0 S, plus we are having constant term on left hand side, that is omega n square. So now we can compare all these terms from left and right, and we can write our expression here. So here S square we are having A plus B, and that is equal to 0. With S we are having 2A zeta omega n plus C, and that is again equal to 0. And for constant we are having A omega n square, and that will be equal to omega n square. So from here we can make out that A will be equal to 1, because omega n square will get cancelled. And now similarly from this equation we can get B is equal to -1, because when we substitute A is equal to 1 and if we take it to right hand side it will become -1. So we will be having B is equal to -1. Now let's substitute here with this equation so that we can get the value of C. So here we will be having 2 zeta omega n plus C equal to 0. So here value of C will be equal to -2 zeta omega n. So now we got all the constant value. Now we can substitute and get the expression here in this equation. Say it is equation number 1. So now we can write C of S is equal to A we got as 1, so it is 1 by S, plus we got B as minus 1, so it is minus S, and similarly we got C as minus 2 zeta omega n. So we can write it as minus 2 zeta omega n divided by S square plus 2 zeta omega n S plus omega n square. Now here we can further simplify this expression as 1 by S. We can take minus sign common, so it will be minus, in bracket we can write it as S plus 2 zeta omega n divided by S square plus 2 zeta omega n S plus omega n square. Now here we can take easily inverse Laplace of this term, but we cannot apply the inverse Laplace to this expression. So let's simplify this one further. What we can do, we can try to make this denominator a whole square. So let's do that. So now let's treat this denominator separately and try to make it a whole square. So here we are having S square plus 2 zeta omega n S plus omega n square. So now in order to make this one a whole square, we can use the trick that we have used in our lower class, like last term is equal to middle term square divided by 4 into first term. So here the last term we are going to add and subtract to make this a whole square. So let's determine what will be the last term. So here middle term we are having this value, that is 2 zeta omega n, so we need to take square of it, so it will be 4 zeta square omega n square divided by 4 into the first term is S square coefficient, so it is 1. So here we will be having the last term as zeta square omega n square, because 4 from numerator and 4 from denominator will get cancelled. So now let's add this value and subtract this value from this expression so that we can make it a whole square. So let's write it as S square plus 2 zeta omega n S plus omega n square plus zeta square omega n square minus zeta square omega n square. So what we can do, we can take this term and this term together in order to make a whole square. So we can write it as S plus zeta omega n the whole square plus we are having this remaining term omega n square minus zeta square omega n square. So if we open this bracket, we are going to get these value. Now further we can rewrite it as S plus zeta omega n the whole square plus we can take omega n square common here, so omega n square, and in bracket we will be having 1 minus zeta square. Here this term belongs to damping frequency, and that we write as omega d is equal to omega n under root of 1 minus zeta square. So this term is nothing but the damping frequency of the system. Now let's rewrite this expression as bracket S plus zeta omega n the whole square plus omega d square. Now let's rewrite this output expression using this value as a denominator instead of this value. So it will be equal to 1 by S minus, in bracket numerator will be as it is, that is S plus 2 zeta omega n divided by, now in place of this denominator we will be writing this as denominator, so it will be S plus zeta omega n the whole square plus omega d square, bracket closed. Now again we need to rearrange this term in order to take the inverse Laplace of it. So let's do that. So we are having C of S is equal to 1 by S minus, in bracket S plus 2 zeta omega n divided by bracket S plus zeta omega n the whole square plus omega d square, bracket close. In order to take the inverse Laplace of this term, we can use the some of the properties of inverse Laplace. So let's see what are the properties that we can use here, like Laplace inverse of s plus a divided by s plus a the whole square plus omega square. So this will be equal to e raised to minus at into cos of omega t. So this is the one of the property that we can use. Similarly, we can also use Laplace inverse of omega by s plus a the whole square plus omega square, and this will be equal to e raised to minus at into sine of omega t. So we will be using these two properties in order to find the Laplace inverse of this term. So let's rearrange this value in this way in order to get the Laplace inverse. So it will be C of s is equal to 1 by s minus, now we can separate here the numerator. So here we will be separating the numerator by considering the same denominator. So we will be having s plus zeta omega n as one term divided by s plus zeta omega n the whole square plus omega d square plus zeta omega n divided by again same denominator s plus zeta omega n the whole square plus omega d square. So now here we can see that this term is same as this term. So we can apply this property in order to get the inverse Laplace of this term here. But if we see the second term, it is similar to this one, but not exactly in the same way. So we need to do a little bit of modification so that this term will become similar to this one and we will be able to apply this property. For that we need this omega d to be here, because in order to apply this property, this omega need to be in the numerator. But here omega d we are having only in the denominator. So we need to have that in numerator. So for that what we can do, we can multiply in numerator and in denominator omega d, and of course the resultant of that will be 1 only, but we will be having omega d in the numerator. So let's do that. So it will be equal to 1 by s minus this term will be as it is, s plus zeta omega n divided by bracket s plus zeta omega n whole square plus omega d square, plus here we will be having zeta omega n divided by omega d into omega d upon s plus zeta omega n the whole square plus omega d square. So now we can see that this term is also similar to this one, so we can use this property here. Now let's take inverse Laplace of this c of s to get the c of t. So by taking inverse Laplace, we can have c of t, and that will be equal to the Laplace transform of this term, that is 1 by s is 1, minus in bracket we will be having Laplace transform of this one is e raised to minus at into cos of omega t. So here a is this zeta omega n, so we will be having e raised to minus zeta omega n into t into cos of omega here, that is this term is omega d, so it will be cos of omega d into t again, plus this zeta omega n by omega d is a constant, so it will be kept as it is, and again inverse Laplace of this one will be e raised to minus at into sine of omega t. So let's write that one. So it will be e raised to minus a here again is zeta omega n, so it will be zeta omega n into t into sine of omega here again is omega d, so it will be omega d into t. So this is the output response of second order system when we are using step input. Now what we can do, we can further simplify this one, this expression. So let's do that again. So it will be 1 minus, we can take out e raised to minus zeta omega n t term because it is in both the term. So we will be having e raised to minus zeta omega n t, in bracket we will be having cos of omega d t plus zeta omega n. Now here omega d we can write as omega n under root of 1 minus zeta square, that is the damping frequency, into sine of omega d t. Now here we can cancel omega n from numerator and denominator. Now again we can take common this under root of 1 minus zeta square also, so that it can come out of this bracket. So let's write that one, 1 minus e raised to minus zeta omega n t divided by under root of 1 minus zeta square. So now in bracket we will be having, since we have taken a root of 1 minus zeta square common, so we need to multiply this term with root of 1 minus zeta square. So it will be root 1 minus zeta square into cos of omega dt plus zeta into sine of omega dt. Now again we can further simplify this bracket, taking root of 1 minus zeta square as sine of theta and zeta as cos of theta. So here we are going to substitute root of 1 minus zeta square as sine theta and zeta as cos of theta. So our expression will become C of s is equal to 1 minus e raised to minus zeta omega n t divided by under root of 1 minus zeta square. In bracket we will be having sine of theta into cos of omega dt plus cos of theta into sine of omega dt. So now this bracket is having sine into cos, cos into sine, so we can replace this bracket with sine of these two angles. So let's write our output again. So it will be 1 minus e raised to minus zeta omega n t divided by root of 1 minus zeta square. Now this will be sine of omega dt plus theta. So this is the output. Now here, in order to find the value of theta, we can have tan theta is equal to sine theta upon cos theta. So we are already having sine value as root of 1 minus zeta square. So it will be root of 1 minus zeta square divided by cos value we got as zeta. So therefore, in order to get the theta, it will be tan inverse of this term, root of 1 minus zeta square upon zeta. So here this is our output expression, and of course it will be in the form of C of t. So we can know the response, or we can get the output of the second order system when we are using step input. So at any given time we need to just substitute the time here, we can get the corresponding output. So in this way we can use this expression to get the output of second order system. So once we got the output equation for a second order system, we can also determine the time response specification, that are the parameters that control the response of the system in transient phase, with the help of this output equation. So what we will do, instead of deriving all these parameter, that is time response specifications, we'll directly see the formula that we can use in order to determine the respective quantities. So what we'll do, we'll discuss here the condition based on which we can use the output equation to get the corresponding term. Like here, first is delay time. So we know that delay time is the time required for the response to reach to the 50% of its value. So in order to get the delay time, what we can do, we can put output as 0.5, and based on that we can derive the time, that will be the delay time, and that is given by Td is equal to 1 plus 0.7 into zeta divided by omega n. So this is the formula for a delay time that we can derive by using the output equation, where we are going to consider output as 0.5. Now same way we can determine next parameter, that is rise time. So rise time we define as the time required for the system to reach to the desired output. So desired output in a normal condition is 1. So here, in order to get the rise time from the output equation, we need to substitute output as 1, and then we can determine what is the rise time. So rise time is given by Tr is equal to pi minus theta divided by omega d. So here theta is equal to tan inverse of under root of 1 minus zeta square divided by zeta, and omega d we know it is omega n under root of 1 minus zeta square. So based on theta and omega d, we can determine what is the rise time. Next parameter is peak time. So we can determine peak time from the output equation. As we know that the peak time is the time required for the system to reach to the maximum peak, and that happens in the initial phase of response. So in order to get the maximum time to reach to the maximum peak, we can use the output equation. What we need to do, we need to differentiate it and equate it to 0. And based on that, we can determine this peak time, and that peak time is given by Tp is equal to pi by omega d. So we can use this formula to determine peak time. Now next parameter is peak overshoot. So peak overshoot we can determine by determining the response at peak time, and from that we can subtract the desired output, and that is going to give us the peak overshoot. So generally we consider the desired output to be 1, so that we can use in our output equation to get the peak overshoot. So that peak overshoot is given by percentage of MP is equal to e raised to minus zeta pi divided by under root of 1 minus zeta square, and this value we need to multiply by 100 to get in percentage. Now the last parameter is settling time. So it is the time required for the system to stabilize to the desired output. Now here we know that a response may match with the exact output, or maybe it is within some limit. So based on that we can define the settling time. So generally, whenever we are considering a settling time, there are two tolerance limits that we can consider. One is for 2% and second one is for 5%. So if we are considering 2%, then settling time will be equal to 4 by zeta omega n. This one is for considering a tolerance of 2% of steady state. Now similarly, if we are considering to be 5%, then it will be 3 by zeta omega n. So this one is for 5% of the required output, that is steady state. So in this way, by using all this formula, we can derive the time response specification for the second order system, and all these formula are derived from the output equation that we derived earlier. So now let's revise what we have studied. So we have discussed about the second order system, and then we determine the root of a second order system by considering the standard transfer function, and later on we discuss about the effect of damping ratio, and after that we derive the output equation in time domain for a second order system when we are giving input as step input, and from that output equation we can derive the time response specification, which we can use for studying the performance or the response of any second order system. So with this we'll end this lecture.